Welcome back. In this video, we will finally conclude our first ever hypothesis test. So just a quick recap of what we're working with here. Our initial assumption was that it's believed that 90% of adult Hoosiers know who the president is. And no, I just made that number up. I don't know if that's actually the case. You could conduct your own sample to figure it out, but that is this example. 90% was our population proportion that we assumed was true. We wanted to know if that was actually the case, so we took a sample, and out of 400 adult Hoosiers that we sampled, 376, or 94% of them, knew who the president was. And we performed a one-sample z-test for a population proportion, and we ended up with a p-value of 0.0038. And we are wondering if that is evidence to suggest that the true proportion in all of Indiana is actually greater than 90%. So, let's actually answer the question for once. Just a reminder, these were our hypotheses for the test. The null hypothesis was that the proportion in the population was 90%. The alternative hypothesis, what we're trying to prove, is whether the proportion is actually greater than that. And I think it's instructive to go back to the parallel between trial by jury in America versus what we're trying to do in this hypothesis test. In a trial, we assume that the defendant is innocent, but if there is enough evidence, then that person or those people can be proven guilty. Similarly, in our hypothesis test, as you recall, we started with the assumption that the null hypothesis was true. The null hypothesis was that the proportion was equal to 90%, so we started by assuming that. If there's enough evidence, we will reject that. And the evidence that we're looking for is if our p-value, which was 0.0038, is less than alpha. Less than alpha. If the p-value is less than that number, we will reject this null hypothesis and state that we have evidence instead of the alternative, which is what we were trying to prove. So we are using the p-value as our measure of how much evidence we have against the null hypothesis. The smaller that p-value is, the more evidence we have to reject the null and say that there is evidence for the alternative hypothesis. But let's talk a little bit more about alpha. So we will make our decision about whether the null hypothesis is appropriate based on whether our p-value is less than alpha. The significance level, which is denoted by the Greek letter alpha, represents the probability of rejecting the null hypothesis given that the null hypothesis is true. Now, if you think about that for a second, the probability of rejecting the null hypothesis given that it's actually true, that seems like something you shouldn't want to do. And in fact, you're right. We don't want to reject the null hypothesis if it's true. We want that probability to be as low as possible. It'd be great if it were 0, but we'll talk more about how we can mess with this probability a little later in this unit. For now, all you need to know about alpha is that it's the significance level, and it's how we compare to the p-value to determine what our decision is for a hypothesis test. For any hypothesis test you conduct, the significance level, alpha, should be specified at the beginning. You need to know what alpha is before you do any of the mechanics of the test, before you calculate your test statistic or find your p-value. Usually alpha is 0.05, and I say that in terms of the problems that you might be seeing in this class. Alpha can be any number from 0 to 1, technically. We usually want alpha to be fairly small because as we saw here, it's really the probability that you make a certain type of mistake when you reject the null hypothesis when it's actually true. We usually want that to be pretty small. You might see alphas of 0.01, 0.001, 0.1, 0.03, usually pretty small numbers there. And if you don't see alpha when you're doing a hypothesis test, if it doesn't state what alpha is equal to, you can assume that it's 0.05. That is the standard. All the other values of alpha are less common. So if you don't see it, it's 0.05. The reason you need to know what alpha is at the beginning is if you don't know that and you specify alpha after you already know your p-value, then you could always reject the null hypothesis. You could always say you have evidence to prove what you want. Just make alpha bigger than your p-value. That's all you'd have to do, and you would always prove what you want. This is called p-hacking, and that's beyond the scope of this course. There are some evil people in the world who change alpha after they get their results, and it makes them look good. Because you usually, if you do a hypothesis test, you're interested in rejecting the null hypothesis. It's not very sexy to fail to reject the null. It just means, what we already thought was true is still true. We haven't really learned anything. But you need to specify alpha before the test. Because alpha, what it is, could change the results of the test. So have integrity, be an upstanding citizen, and always specify your alpha before you start your hypothesis test. So now we know a little bit more about the significance level, alpha. And we said here, if the p-value is less than alpha, and alpha is usually 0.05, that means we reject the null hypothesis. And really there are only two things that can happen at the end of a hypothesis test. There are only two decisions that you can make. If the p-value is less than alpha, as we said, you reject the null hypothesis, and you'll conclude that there is evidence of whatever the alternative hypothesis says. So, if our p-value is less than alpha, we'll reject the null hypothesis, and for the example we've been working with, if that's the case, if the p-value is less than alpha, we will conclude that there is evidence that the true population proportion of adult Hoosiers who know who the president is greater than 90%, which is different than what we assumed going in. We assumed it was 90%. But if the p-value is less than alpha, then that's saying our sample provides strong enough evidence. Our sample proportion was so much higher than the population proportion we assumed that this is actually not accurate, and p is actually somewhere bigger than that. The other option that can happen, the other decision you can make, if the p-value is greater than alpha, say you've got a large p-value like 0.4 or something like that, anything bigger than alpha, you will fail to reject the null hypothesis. And you'll conclude that there is not evidence of the alternative. So if we got a larger p-value than alpha, if alpha is 0.05 and your p-value is like 0.1, the p-value is bigger than alpha, then you're saying, well, our sample results aren't really that extreme. It's not super likely that our sample means that the true proportion is bigger than what we thought it was. It's not unusual to just say, hey, the null hypothesis seems reasonable here. We don't have evidence of what we want to prove. That's the case if the p-value is bigger than alpha. Some of you might be thinking, well, what if the p-value is equal to alpha? Remember how we calculate the p-value. We're finding the area under the normal curve. We're using normal CDF. When you use normal CDF, the area that you get, the calculation, the number, is usually a really long decimal, right? Technically, that decimal goes on forever. It's non-repeating, non-terminating. That p-value is never going to be equal to alpha. It's not. In all my years of doing stats with hypothesis tests, I have never once had a p-value exactly equal to alpha. It's going to be one of these two. It can be close. You can have a p-value of like 0.05001, but then if alpha is 0.05 and the p-value is 0.05001, you're here. So don't worry about the p-value being equal to alpha. It's never going to happen. It's either going to be greater than or less than. These are the only two things that can happen. And based on that relationship between the p-value and the significance level, that tells you what decision to make and whether or not you have evidence of the alternative hypothesis. Some of the more grammatically sound of you might be thinking that failing to reject the null hypothesis is like a double negative or something. It just doesn't sound right. So why are we saying we fail to reject the null hypothesis instead of just accepting the null hypothesis? Don't those mean the same thing? The answer is no. They do not mean the same thing. Going back to the trial by jury comparison to the hypothesis test, this is yet another parallel between the two. In a trial by jury, if there is not enough evidence to prove that the defendant is guilty, what does the jury find the defendant? Not guilty. They never say, we prove the defendant innocent, because you can't prove innocence. Maybe there's an alibi. I don't want to get into law here, but juries don't find defendants innocent. They find them not guilty, because the whole idea of the trial is whether the person is guilty or not. You can't really prove innocence. It's the same thing with a hypothesis test. So a quick review of the parallels here between a trial by jury and a hypothesis test. In a trial by jury, we assume the defendant is innocent. In a hypothesis test, we're assuming that the null hypothesis is true. In the trial, if there's not enough evidence of guilt, the defendant is found not guilty. They never say that they're innocent. Similarly, in the hypothesis test, if there's not enough evidence of the alternative hypothesis, which is when the p-value is greater than alpha, then we fail to reject the null hypothesis. For the same reason we don't find the defendant innocent, we don't accept the null hypothesis. Mainly because, how could we? Based on just taking a sample from a population, how can we prove that the population proportion is 0.9? We can't prove that unless we get data from every single individual. So we can't ever accept the null hypothesis because we don't know what p is. All we did was take a sample. We can't accept the null hypothesis, but we can fail to reject it if we don't have evidence of the alternative hypothesis. So this is your first friendly reminder, potentially of many, that we never, ever accept the null hypothesis. We can't. We can never say that p is equal to a particular value. We can't know that based on a sample. So just don't do it. You either reject the null hypothesis or you fail to reject the null hypothesis. If you ever say that you accept the null, I will find you and you will pay. Don't do it. There's a list of things you should never do in this class that this is on. You should never use normal PDF to calculate area. You should never assume that correlation implies causation. And you never accept a null hypothesis. It's on that very short list. If there are other things I should add to that list, let me know. Leave it in the comments of the video or let me know in an email or something. I'd like to make a list of things that you don't do in AP Stats. That's definitely on there. So, now that we know that, suppose we set alpha equal to 0.05 for the example we've been working with the adult Hoosiers and knowing who the president is. Okay? Setting our significance level, alpha, equal to 0.05 means that we are tolerating a 5% chance of rejecting the null hypothesis and concluding that this is true, that the population proportion is actually higher than 90%, even if the proportion truly is still 90%. So that would be like wrongly concluding that the proportion is higher than it actually is. Okay, that is an interpretation of what alpha is saying. If we set it at 0.05, there's a 5% chance of making that mistake. for that error. Okay, and we will talk more about that a little later. We're going to get super into the different types of errors you can make in testing, but let's get back to this example first. If alpha is 0.05, and remember our p-value is 0.0038, do we reject the null hypothesis, or do we fail to reject it? Somewhere on here is the answer. We know we're comparing the p-value to alpha, right? This is what we're looking for. If the p-value is less than alpha, we'll reject the null. If the p-value is greater than alpha, we'll fail to reject the null. So, which is it? The p-value is 0.0038. Alpha is 0.05. Which way does it go? 0.0038 is smaller than 0.05. So the p-value is less than alpha. This means we do what to the null hypothesis? Reject or fail to reject? P-value is less than alpha. We reject the null hypothesis. So, you might recall in the last video, there were 5 steps to conducting a hypothesis test. The last step was stating your decision and conclusion. Once you've calculated your p-value, you should already have alpha from the very beginning. You'll be able to make this comparison. Your decision is whether you reject the null hypothesis or fail to reject it. Your conclusion is, what does it mean to say this? What does it mean to reject the null hypothesis in the context of the problem? Here's what you can say. We now know that by comparing the p-value to alpha, we can come to our decision. What does it mean? How do we conclude our test? What have we learned from our sample? Here's a template for how to conclude your hypothesis test. With a p-value of whatever the p-value is, which is either less than or greater than whatever the value of alpha is, your significance level, we either reject or fail to reject the null hypothesis. There either is or is not evidence that whatever the alternative hypothesis says in context. Okay? Now, these things that have 2 options, what you say here depends, or it makes you pick one of these. So if your p-value is less than alpha, then you reject the null hypothesis, and there is evidence of the alternative. If the p-value is greater than alpha, you fail to reject the null hypothesis, and there is not evidence of the alternative hypothesis. So, if you're feeling adventurous, I'd like you to go ahead and use this template to conclude the hypothesis test for our example. You should be able to plug in what you need. The only thing that's really not right here is what the alternative hypothesis means in context, but you could give it a shot. So if you want to try it, go ahead, pause the video, give it a whirl, come back when you're ready. If you want to go through it together this first time, I totally get it. Let's get started. So we could say, to conclude the hypothesis test for our example that we've been working on for like 3 videos now, with a p-value of, our p-value is 0.0038, and we've concluded that that is less than alpha, and alpha here was 0.05. When you write it this way, it is understood by professionals that your p-value is this one, obviously. This is the significance level, alpha. We all understand that. Okay, you don't have to say anything else here. This is enough for this part. We said that if the p-value is less than alpha, we reject the null hypothesis. If we reject the null hypothesis, that means there is evidence of the alternative. There is evidence that. Now, this is really the only tough part, in my opinion. Writing out what the alternative hypothesis means in the context of the problem. Right. So you need to know what the alternative hypothesis is first. That was that p is greater than 0.9. Now, you can either try to explain in words what this means, or you could look back at the question that was being asked, and chances are that's what you need. So the question was, is this evidence that the true proportion is greater than 90%? That is what the alternative hypothesis is saying, that the true proportion is greater than 90%. I've done a bad job here and didn't include the context of the problem. The true proportion of what? Well, it's evidence that the true proportion of what? What is it the proportion of? If you don't specify, then it could be anything. It could be gray snails on the sidewalk. It could be the proportion of students who say the word when they're speaking in front of the class. The proportion of what? It's so important to put that context into this conclusion. Otherwise, it's meaningless. The true proportion of adult Hoosiers who know who the president is. The true proportion of our population. The true proportion of adult Hoosiers who can identify the current president is greater than 90%. We can come up with a very solid conclusion to our test. The original question was, is our sample evidence that the true proportion is greater than 90%? Well, with a p-value of 0.0038, which is less than the significance level, our cutoff, we reject the null hypothesis. There is evidence that the true proportion of adult Hoosiers who can identify the current president is greater than 90%. This is clear, it's complete, it's concise, it's in context of the original problem, it's got all the C's. I wrote it and I'm Seplik. That's 5 C's, that's so many. I would highly recommend using this template for concluding your hypothesis test. I know we've only done one so far. It's not exactly a pattern yet, but trust me, we are going to do plenty of hypothesis tests. If you use this template, you can't go wrong. This will get you where you need to go every single time. So I hope that you can use that to your advantage going forward. If you're anything like me, you're probably like, okay, cool. We got a conclusion. We're done with the test. This is great. Now I know how to do it. And that's great. I'd be super happy if everyone could go through all the steps of the hypothesis test appropriately. Naming your hypotheses, checking your conditions, stating your model and the test that you're doing, calculating your test statistic and p-value, making your decision and conclusion. Let's step back. Why did we reject the null hypothesis? Because the p-value was less than alpha. What does that have to do with anything? Remember when we interpreted the p-value and we said that the probability that we get a sample proportion at least as high as we did, given that the null hypothesis was true, was only 0.38%? That's super low, right? Assuming that the null hypothesis is true, what we saw in our sample was really strange. That's why we're rejecting the null hypothesis. Because it was so unlikely. It was less likely than the cutoff value that we determined. Okay? Anything up to 5% would have led us to reject the null hypothesis and conclude evidence of the alternative. if there was an 8% chance of getting a sample proportion at least that high, 8% is bigger than alpha, we would fail to reject there and say there's not evidence of the alternative. So I hope that brings things together a little bit. This is not just a series of steps meant to be done and then discarded. This is telling a story. And I feel like just being able to write it isn't the whole thing. If you can truly understand why we're rejecting here, why we're saying there's evidence of the alternative, it's because if that null hypothesis were actually true, the chances of seeing what we did in our sample are very small. What does it mean to be very small? Smaller than this. That's all we need. So, in the next video, we are going to talk a little bit more about p-values, how big or how small they are, and what it means in terms of your test and the evidence you have with your sample. And then we're going to do another example. We're actually going to do 2 more hypothesis test examples over the next few videos. And I'm hoping that between the one that we've just completed and those 2 others, that you'll be able to see a wider array of the things that are possible when you do a test like this. We're still using one sample z-test for population proportion. We will get into different types of scenarios later on in the unit, and then in Unit 7. But for right now, I want you to really start to crystallize the idea of a hypothesis test. If you've taken good notes the last few videos, those next examples should go a lot easier. And then when you work on them on your own for homework and quizzes and tests and the AP test, by the time you get there, it should be pretty automatic. That's the hope. So, we're done with our first test. We'll look at some more starting in the next video, and we'll see you there. Take care.